Hello. So today I want to talk about an interesting bug that I ran into recently while working with C++, and it kind of taught me an interesting lesson in object lifetime and how it works in C++. So just a breakdown of what I intend to show is first I'll introduce the program, talk about expected behavior, and then we'll run it and see what the error behavior is. Then I'll start the program using GDB, our Linux debugger. Then using GDB, we can analyze what's going on with the program and hopefully explain the behavior. And then finally, we will write a fix for this behavior, and then we can validate it using GDB again. So let's go ahead and get to it. Okay, so here's the code we're going to be working with today. We have one function called return JSON string, which just returns a std string, which is basically just a string representation of some JSON object we might have somewhere. So as you can see, we call that in our main function. And suppose for one reason or another we need a char pointer instead afterwards. So in this case, I'm using printf, which is a C function. C does not know what a std string is, so we actually have to pass it a char pointer. That's why I'm using C string here. So we'll create that string object, create a pointer to that, and then store it in this variable. And then in this line, we'll use that char pointer to print out the object that we just stored when we called this function. So as you'd expect, line 9 here would print out receive char pointer, and then we'd expect this string JSON object to be printed out. So let's see what happens when we run our program. Okay, so now that we're ready to run our program, let's go ahead. I'm going to use G++ to compile our program into an executable called printstring. So as you can see, our printstring executable is there. So just a quick reminder of what we expect is that on line 9 we expect to see this line will print out receive char pointer, and then we should expect to see this JSON object, JSON string representation printed out. So let's go ahead and run printstring. And as you can see, it printed out garbage. And if we try again, keeps printing out randomized garbage. So question is, what is happening here? Okay, so in order to really figure out what's going on, we're going to use GDB, which is a Linux debugger, in order to step through our code and see what's going on. So first off, I need to recompile with debug symbols. So I'll recompile my print string executable, and I can run it with GDB. And that will start up the GDB program using this print string executable. First thing I'm going to do, this is just a personal thing, but I like to use Intel assembly just because it's more familiar to me. But so we've established that there's some kind of problem occurring between line 8 and 9 here. Like our memory somehow, the object in memory is somehow becoming corrupt, and we don't know what's going on. So I'm going to set a breakpoint on line 8 so that we can step from there and figure out what's going on. So I'll do that like this, B8. And then one other thing is I'm going to display 10 instructions relative to the program counter. So basically what that's going to do is every time I run a step after my breakpoint, it'll show 10 instructions after where the program counter is. So we'll be able to see the instructions that are going to be executed as we run our program. So now we can go ahead and run. And as you can see, we've hit our first breakpoint on line 8 here, right here. So now one extra thing I'm going to do is I'm going to also display the string value of our variable char pointer, so that I can always, every step it'll show this value, and I can see what'll happen at every step, how it gets populated, how it gets corrupted, etc. So now we've got our displays enabled. We can start stepping through our program. Okay, so we'll start stepping through our program instruction by instruction, starting from the program counter here, the little arrow. So we'll step in, and I want to step into this function here, which is return JSON string. You can kind of recognize it after the C++ name mangling, but that's going to be return JSON string that we call on line 8 here. So I'll step into that. As you can see, now we're in our function call return JSON string, and there's one thing that I want to call attention to here, step over this function, is this function call here. So we step in, and we can see that this is the constructor for a basic string. Basic string is, a stud string is kind of like just an alias for a basic string. That's like the base object that's created. Yeah, so a stud string is basically just an alias for this big long signature to create a basic string. But so this is the actual object being created in memory here on line 4 when we create this string. It's creating the object in memory. So we're seeing that basic string constructor here. So that's all I really wanted to show here. So really quick, I just want to show BT shows the stack trace, so we can show that we were in main, called into return JSON string, and then we're in our constructor for the basic string. So I'm going to finish this function. If I call BT again, you can see that now we're back in return JSON string. And I don't have anything else that I want to show within return JSON string, so I'll actually finish out of this too. So now we can continue with our program. Okay, so we just finished our call to return JSON string. Let's keep stepping through into this function call here, which is call to cstring. So this is actually just going to get a pointer to the object that we just created in memory with return JSON string. So I'm going to go ahead and finish out of that, bringing us back to main. So just one thing cool that I learned recently is you'll notice that the char pointers, we finished our call to cstring, but our char pointer is still not populated. So why is that? Turns out there's actually one last instruction that has to happen here. This is a move, so it's going to move memory from one location to the next. It's a move operation, moving the data in RAX to RBP minus some number. So RAX is actually a named register that's often used. It's the name of the 64-bit register that's used to hold the return value of functions. So I can actually show if I did x/s on RAX, I can show that it actually has the value of the JSON string, but has not been put into RBP minus some number. RBP is the base of our stack pointer. Okay, and just below, so minus some number, just below the base of the stack pointer, the base pointer of the stack, is where local variables are stored. So that local variable, RBP minus 0x38, is actually our char pointer. So we should see that if I step over this, or after this instruction, we should see that our char pointer is populated. So let's go ahead and see. And amazing, just like that, yeah, it moved the value from RAX into that local variable. So that's pretty cool. Now, it looks like everything's fine. We have the string as we expect it in char pointer. We can see this printf being called down here. That's the printf that's called on line 9. So something is happening between our program counter and down here that is corrupting our memory. So let's just keep stepping through to figure it out. Alright, so where does everything go along with this program? Let's keep stepping through into this function call here, and you can see that this is actually a destructor for the basic string. So if you remember on line 4, we called a constructor for the basic string to basically store the object, to create the object that is this string that's returned by return JSON string. And actually, if I step through a little bit, I can step over to here, and I can see that this is the C++ delete call. This is like pretty much the equivalent of C++ equivalent of C's free call, as I understand it. But so as we finish out of this function, you can see that now we're on line 9 of our source code, but our memory is corrupt. Our char pointer no longer holds that string object that we wanted. So what happened? So basically C++ called the delete function right here at the end of line 8. So the lifetime of this string object was right up until the end of pretty much until this semicolon, and then it got freed, and then that's why we lose it. So my only understanding, or my only like logical reasoning for this, is that C++ creates an object using return JSON string, and I guess it figures that after this line, there's no way for anything else to reference this object, this block of memory that we created, unless we've created a reference to it. But here we've only created a reference. We only created an object that stores the pointer itself, but not the actual object. So the way to fix this is actually we can create a std string, let's call it JSON, and we'll assign that to return JSON string, the return value of that, and we'll return this, or we'll replace this with our JSON variable, and let's see if this helped. So we'll go ahead and recompile our program with that change to the JSON we just made, or to the adding the JSON new JSON variable. We'll recreate this print string. Oops. And let's go ahead and run it, see if our behavior has changed. And look at that, it's working now. So what this kind of taught me is that you need to take care of, the lifetime of your objects that can be overlooked, and you could be referencing garbage eventually. So it's kind of an interesting lesson that was a great use of GDB, and hopefully I presented it in a way that most people could learn something. But yeah, this is a really cool problem I ran into, and thanks for watching. Also, one last thing I wanted to include in here, just another thing that I learned through this, is this bug behavior only happens if the string is sufficiently large. So if I use some really small string value, and I go ahead and recompile, and so this is the original program that doesn't have the bug fix included, right? So we should see that it doesn't print ABCD, but clearly works. ABCD is printing fine. I learned that this is related to something called small string optimization in C++. And this is basically that when strings are sufficiently small, the entire object is stored on the stack. So it's a little bit different with the strings being larger. I think the threshold is either 8 or 16 characters. It will store that object on the heap, and then we need a reference to the heap, and that's why we get this issue. But with this, it's storing the entire object on the stack, so that's why this behavior does not happen. So just in case you wanted to recreate this for yourself, make sure to use a string that is sufficiently long.